All right, you can start.
Okay, thank you very much. Good afternoon, everyone. Welcome to today's session. And as it is on your screen, I will be discussing about cross-validation and bootstrapping. So please don't hesitate to ask question if anything is not clear, and you can also please let me know in case my presentation goes off. So a little bit of the content. First, I'm going to go through cross-validation, the definition method, and the types. Also, bootstrapping. Under that, it will just be the definition and application. So, what is cross-validation? Of course, I will be lying if I say you won't be truthful enough if you guys say you haven't had anything about cross validation. Of course, you've used cross validation in the past few weeks in your task, in the various tasks you've been given. So but I'll just give a kind of a revision and maybe ascertain some of the things you've known, and maybe make clearer some of the things that are not clear. So cross validation in general is a model selection method. You have numerous model, then you want to have a kind of criteria to select the best one out of the models you have, right? So it's a model selection method. It's a kind of method for estimating the general performance of your model. So when you build your model, what you want to do is to know the general performance of your model, right? Not only the performance on the training set, because you build your model around your training set, right? But you want to know the general performance when you deploy your model out there. What is a kind of information in terms of the performance of your model when you deploy it out there? That is what cross validation actually gives you, right? So what are the basic method for CV cross validation? So the first thing, the procedure here is, the first you partition your training data into K subsets. So you can just follow the pictorial representation here, as you can see on your screen. Can you still see? Okay. If you can't see, if you can't see the screen, just let me know. I think I lost connection.
Yeah, it has gone. We can't see it anymore.
I'm going to just quickly bring it up again. I'm always having this problem. So, and up it is. So now, like as I was saying, you just follow the pictorial representation. So you partition your model, your training data into K subsets. So in this image, we have how many subsets here? There are 5 subsets here, right? Of the training data, we have 5 subsets. Just look at a column where you have I'm not good with colors, but I know there is one with like maybe like green. I know it's not green. I'm not good with colors, and the other like yellow, right? So the first 4, which is in green, and the last one, which is like yellow. So there are 5 partitions in total. So K subset here represent K equals to 5. So you train your model on K minus 1 subset. So you take one out of those subset and train your model on K minus 1 subset. So this is what the green colors of the boxes represent. So, and it is label here, the training. So you train your model on those subsets, and you evaluate your model on the other subset, which is the last one here, the validation depicted in yellowish color here, right? So now you move again, you take a different subsets, you train your model and you do validation. So this is what cross validation is in general. So just follow the picture and you see that at every point in time there is a different subset for the training set and the validation set, right? So this is how cross validation procedure is. And in the end, after you've done all this, you train your model across the different subsets, then you compute the generalization error. And the generalization error, I've written the formula here. It is just the expectation, which is like basically the mean, right? The mean over the loss function you might choose. R there is the loss. The R there might be your mean square error, depending on the kind of model. It might be your mean square error. What kind of error might you have? I don't know. So many errors function there. So R there is just your error function. So the error function is a function of your model and the subset, the training subset, right? So you calculate the error over the different validation sets and you find the mean. So this is your generalization error as it is here. Uh, what are the types of cross validation that we have? Of course, the procedure I listed out earlier is the k-fold, right? That is known by everyone here, right? We know the k-fold. So you divide your training set into k-fold and you train on k-1, validate on the last one. So this is what k-fold is. Okay, this is gone again. Let me quickly bring this up. So the k-fold, now. Now the other
So the
one,
presentation has gone.
yeah, it's
Okay,
it's
it's
up
coming. It's
now.
coming.
Yeah. So
Yeah, it's
now
fine now.
okay, thank you. So the k-fold now, I've explained using that procedure. Leave one out cross validation. There's another type, leave one out cross validation. This is also a kind of k-fold. But now I want to throw a question to you guys. What is k in this? If you have your training set, there are like 100 data points in your training set. So what is k here in when you are talking about leave one out cross validation? Anyone with the answer? What is k when you're talking about leave one out cross validation? I'm expecting a comment.
I think K might be anyone you decide to choose.
Uh, now, let's say you have 100 data points. Leave one out means that you want to train your model on 99 points and validate on 1 point. That is leave one out. You are leaving one out of the training set in order to validate on that one, right? So now what is K when you're talking about K fold? What is K here? K here is just exactly the number of data points in your training set. Exactly. One you got it right. Is the number of sets in the training data. So if your training data is n, which is 100, let's say 100, then k fold here, your k also is 100 because you want to train on k minus 1. 100 minus 1, that's 99 data points. You want to train on 99 data points and validate on just one. So that is like leave one out cross validation. I guess you all understand that, right? So that's leave one out cross validation. There's another one that is not popular, but is also worth considering, and that is hold out method. So this hold out method can be any kind of design that you want, which is not necessarily k-fold. K-fold, the partition are well organized, right? In k-fold. But hold out method, they are not necessarily organized. It's just a kind of design method that you come up with. Example of such is even versus odd design point, whereby you take the even point, even that's 2, 4, 6, 8, up to the last data point. You train on the even and you validate on the odd. You do that, you reverse the case, you train on the odd and you validate on the even. I hope you guys understand that. So that is a kind of even versus odd design point. So it's a kind of odd out method example. So you can design any kind of odd out method that you want. So it's up to you. So these are basically a few types of cross validation method that types that you might have or you might design. So that is that about that. So now let's move to bootstrapping. Bootstrapping is a resampling technique, right? As mentioned here, for estimating the parameter of the population. So what do you mean? But every time we build a model, we want to maybe find the parameters that are best to predict into the future, or any kind of thing. You might want to calculate a kind of quantity in any kind of design or any kind of model setup. The main interest is probably to calculate a kind of quantity, right? That might help you in your future, maybe prediction and anything. So now bootstrapping is just a kind of procedure for calculating that quantity, right? So the procedure are also spelled out here. The first step is to select n samples. Let's say I will basically give a kind of scenario here. Let's say you have students in a university, right? In a university, there are like thousands of students. Of course, there are thousands of students, and let's pick public university in that case, thousands of students, and you want to find the average height of students in that university. In order to measure the height of every student in that university, thousands of students, it will take like days, right? In order to do that. And you might even encounter error and not it's not advisable to go through. So that's like a population of students in that university, and you want to estimate a quantity, and the quantity is average height of the students in that university. Is costly and time consuming to measure the height of every student in that university. So you won't want to do that. So what you might do bootstrapping to estimate the average height and just follow the procedure. You actually select n samples with replacements. Let's say out of those thousands students in that university, you might select, say n is maybe 100 or 50. 50 you can manage, right? You can manage 50 students. You just select randomly 50 students with replacements, not with replacements. You select 50 students, then you compute the required quantity. And in this case, that is the height, right? You take the height of every student in that 50 sample, and you compute that quantity being the average, right? Average height, average of those 50 students. Then you repeat step 1 and 2 k times. So you select a different sample with replacement also, compute the average height of those sample again. You do that a number of times, let's say k times. It might be maybe 100 times or 80 times. You do that repetitively. Then in the end, you now compute the overall mean of those k times parameter estimates. So this is what step 4 is saying here. So you calculate the mean of the computed quantities, right? And you know the formula for the mean. And the idea here is that after doing this bootstrap method, the idea here is that now the quantity you end up with after going through this procedure is approximately equal to the average height of the students in that university. So this is just the idea of bootstrapping. So the idea here is just the law of large numbers that you might have heard of, which says that when k tends to infinity, when you repeat this procedure k times and k is extremely large, like close to infinity, then the limit of the expectation of the quantity you calculated is approximately the same as taking measuring all the students in that university and taking their average height. So the experiment here, the quantity from this experiment here is the same as the population parameter when you perform this experiment k number of times, and k is extremely large, maybe close to infinity. So this is what law of large numbers large number is. So this is bootstrapping procedure. Now I'm going to leave you guys to bring a kind of scenario where this might be applicable. Of course, I mentioned one, I think 2 weeks ago when we were discussing, was it something about SGBoost random for assemble method, right? If you could still remember. So what are the application of this? Application of this, can anybody just give me one application of this bootstrapping procedure? Waiting for your comments. I remember I mentioned one the last time we were talking about SGBoost assemble method. So there is this bagging method, whereby this bagging method you train. It is used by random forest algorithm, whereby you iteratively select features. You build a model on those features, then you assemble the performance of the models together. This is one application of bootstrapping. So bootstrapping is used there. Let me see if I can still find. Let's see. So if you can, let me put this in presentation mode so that you can see this clearly. So let me just open. So so here, if you can see the pictorial representation under bagging, example here is random forest. So the very first where we have a training subset 1, 2 up to training subset M, this is a bootstrap procedure whereby you randomly select a subset of features from the overall feature space. Yeah, you train different model on different subsets. So this is what's a kind of application of bootstrapping method. So this is popularly used in random forest algorithm. So another thing is where you can also perceive bootstrapping as a cross validation method, right? If you think about it, this is also a kind of cross validation method, whereby you randomly select some subset of the feature space, then you train your model on that, then you find maybe the error, you select a different subset, right? You train your model, then you validate your model on other subsets that are not selected. So this is, you can also perceive bootstrapping as a cross-validation method. So I hope this explains what CV and bootstrapping is. And cross-validation is popularly used, of course, especially in statistical machine learning, but it is not popular in deep learning procedure. Can anyone just tell me why cross-validation is not that used in deep learning? Of course, you might not have a lot of maybe idea about deep learning, but maybe you've heard about why it is not popular in deep learning method. Why cross-validation generally is not used in deep learning. Anyone? Outliers? Well, not necessarily. So if you've heard of a lot of deep learning algorithm, you know that the training process of most deep learning algorithm is very costly. Like it might take days to train some deep learning algorithm. So let me go back to uh, so now let see this first training subset, the first column here. You train your model on the first four, and let's say you are using deep learning, and it takes like maybe days to train this very first column, right? It takes days. Then after getting your trained model, you validate. Do you want to also go ahead and use days to train the second set, right, of the fold? You don't want to do that, right? If it takes like maybe a week to train your deep learning model, so now using this fold, how many weeks are you going to burn out to train all this model in the end using like this is how many fold now? This is 5-fold CV, right? So you will take 5 weeks because just training take a week. Then in order to do 5-fold cross validation, you will be using like 5 weeks, right? In order just to train one model. So that is why cross validation generally is not popular in deep learning. So in deep learning, you only divide your set into training and test. So you just make sure that you get all the parameters right. You make sure you do a lot of research in order to know how to tune your parameter in the training process, because you don't want to train multiple times because the training procedure takes long, right? You don't want to train multiple times in order to do your cross validation. So, but if your training, if your algorithm is not that costly, maybe you're just using a simple linear regression, you can afford to do all this cross validation for model selection, right? You can do that maybe for simple linear regression or some uncomplicated algorithm like that. Also, one of the types of CV, which is the leave one out cross validation. The reason why that is also not popular is because it is also costly, right? Let's say you have 1 million data points. Can you do leave one out cross validation on 1 million data points? Obviously, you can't do that, right? Because that means you'll be training your model how many times? 1 million times. Because if you are doing leave one out cross validation, you train your model on 999,999 data points, then validate on the last one, which is the 1 millionth data point. Then you do this multiple times, like 1 million times. You obviously, yes. The presentation is gone. So you obviously don't want to do that. You don't want to. So in order to cross validation also has its method of choosing the right fold and maybe knowing when to perform cross validation and when not to do when not to do this. In deep learning method, you don't even want to do this, right? And for some data points, you know some data points you just want to do twofold: train on a set and validate on the other set, just twofold, right? And some, it might require you to do maybe 5-fold or 10-fold, depending on how large your data point is. So I hope this explains or give a little bit of more understanding around cross validation. So if there is any question, I will take them now. Thank you. There's a question about most algorithm in deep learning are black box model. Yeah, of course, not necessarily most, but a larger percentage, of course. But now there is this field of algorithm explainability, right? So this is a kind of field in deep learning that is dealing with explainable algorithm, how to explain most algorithm that are said to be black box, right? And if you say black box, of course, people code them up, right? Of course, they have some procedure to come up with the code, but sometimes you just don't know why some things work. So that is why it is proclaimed as black box, because you code it this way, but you don't know why you are getting some of the results. So it is somehow black box. So any other question, comment, or maybe some additions to what I've discussed?
Any question?
Welcome. Thank you very much. I think there is no question.
Oh, okay. So if there is no question, thank you very much, Usman. So I will just stop the record.
Okay, thank
And
you.
thank you, guys.
So see you guys later. Thank you.